Good evening, everyone. Welcome to our fourth webinar of CGCA 2024. And today's topic is about theoretical chemistry, and we are very pleased to welcome our first speaker, Professor Zhenggang Lan. He was a very senior scientist in the field of theoretical chemistry. He got his PhD in the Technology and Technical University of Munich under Professor Wolfgang Domke in 2009, I think, right? Then he moved to München under another big name, Professor Walter Thiel in Max-Planck-Institute of Core Research. Then he moved back to China at 2011 to become one of those 100 talent program researcher. In 2018, he became a professor at the South China Normal University. His research focus is on the theoretical chemistry and the spectroscopy. Today, he's bringing our his recent research on the name of non-adiabatic dynamic and machine learning. Please go ahead, Zhenggang.
Yeah. So, hello, everyone. So I should say good evening, and as well as I think good afternoon, maybe more good morning. Anyway, yeah, for all the participants. First of all, I would like to thank the organizer, particularly Wenlan Liu, for his kind invitation. So I'm very happy to give this, take this opportunity to discuss some of our recent work in this CGCA conference 2024. Particularly now is still the Spring Festival time. I should say happy for Spring Festival for all the listeners today. Yeah. So before the starting of my talk, I think I should say hello to everyone because I stayed in Germany for quite some years, totally I think less than 8 years. So I went back to China also, came back to China also in 2011. So now it's also many years. So this is why I'm very happy to get contact with Wenlan again. And in the future, I think if some of the new friends want to go back to China, or also want to visit my city, anyway, please contact with me. I will be very happy to become a host. Okay, so anyway, it's good to know the new scientist. So today I would like to talk about some of my work on the non-adiabatic dynamics and machine learning. So I'm a theoretician. So today, instead of giving a very complicated formula, I decided to talk about more pictures. And let's try to provide you some of my understanding on the photochemistry and the photophysics. Okay, so first of all, I would like I will say my research interesting is photochemistry and the photophysics. So in our world, we have a lot of photo-induced chemical reactions. So I'm a theoretician, so I'm interested to developing methodology, method and computer software to simulate all of these photo-induced reactions. As we know, normally when the systems stay on the ground state after photoabsorption, it will go to the molecular excited states. On the excited states, the system can maybe go from the high vibrational level to the low vibrational level, giving the so-called vibrational relaxation. And also from the lowest vibrational level, it will emit a photon to the ground state. This will give us so-called fluorescence. I think many people are familiar with the fluorescence. But sometimes the photon can bring the system to the higher excited states, and afterwards, the system can easily jump from one state to another, giving the so-called internal conversion. In some situations, the system will moving from the singlet state to triplet state, giving the so-called intersystem crossing. And from the triplet state, the system may still go back to the ground state. Some of these are giving so-called also give the emission. So anyway, this will give a lot of this is the basic picture about the photo-induced chemical reactions. But this is somehow a simplified picture. In reality, when the system, molecular system are excited after excitation, the system will move on the excited state's potential energy surface. For example, it's moving on this S1 surface. But then, along with the nuclear motion, the different electronic states can easily cross to each other, giving the so-called surface potential energy surface crossing. At the crossing area, the system can easily jump from one electronic state to another. For example, here from upper state to the lower state. Now, this result with the so-called non-adiabatic transition. I think non-adiabatic dynamics widely exist in photochemistry and photophysics. For example, starting from very small compound like ethylene or azobenzene, so we know their photochemistry are governed by non-adiabatic transition from excited state to ground state. Sometimes if we go to the aromatic system in the solution, for example, we also say a lot of the non-adiabatic dynamics. I know many people are familiar with the transition metal complex. So nowadays, many people are starting the so-called OLED. So for the OLED materials, sometimes you have to use a transition metal complex. For this transition metal complex, their photochemistry also involved the surface crossing, for example, from the singlet to triplet, and also the non-adiabatic transition. And also, if we go to the photobiology, sometimes we have a lot of the photostability and photo-induced energy transfer. This also this process is also covered by the non-adiabatic transition at the surface crossing area. In recent years, many groups start to investigate the solar energy conversion. I think no matter whether we will go to the photohubbing system or whether we will go to a photovoltaic system, we also have a lot of the photo-induced energy transfer and the excited state energy transfer or electron transfer. For both of them, I think their essential mechanism are governed by the non-adiabatic transition at the surface crossing area. So this is why I think the non-adiabatic dynamics playing a very important role in the photochemistry and the photophysics. I think we have to start it. But theoretically, I think it's very difficult to start in non-adiabatic dynamics. I think we will face some challenges. The first challenge is when Oppenheimer approximation breaks down, so you have to really treat the coupled electronic and nuclear motion at the surface crossing area. I think this is one of the most challenging in the theoretical chemistry because it breaks the basic principle of the electronic structure calculation. At the same time, we needed to describe the molecular excited states, for example, here and here. I think this is also not so trivial because on the excited state, the electronic wave function become very complicated. So we have to dealing with a very complicated electronic state, electronic wave function. When the system become larger and larger, for example, here and here, then we know we have a lot of the degree of freedom. We have a lot of the atoms. So the complexity itself become very important. So the complexity in the realistic polyatomic system also is a challenge itself for the dynamic of simulation. At the end, we needed to, when we needed to study the non-adiabatic dynamics, we normally use the spectrum particularly the time-resolved spectrum to observe the non-adiabatic transition. But somehow it is also not so trivial to interpret the experiment out of observation. So there, these 4 points are my limited understanding of the current challenge in the non-adiabatic dynamics. So my own research cover from different aspects of the non-adiabatic dynamics. So we're starting from the potential energy surface construction, calculate the excited state reaction pathway. Sometimes we do the quantum different dynamic simulation to really simulate the non-adiabatic dynamics. This trying to understand the electronic motion, the nuclear motion at the same time. In recent years, we're trying to using some machine learning technology to study the mixed quantum classical dynamics. At the same time, recently, we're also trying to study the time resolved spectroscopy. Today, because of the time limit, I will focus on my talk on the machine learning part. I think because the non-adiabatic dynamics, excited states non-adiabatic dynamics is very challenging. So this is why in over last decades, several theoretical groups developed all different kind of the dynamics approach, ranging from quantum dynamics to mixed quantum classical one. But I think the main problem is no matter I mean, although we put quite some effort in this field, but still nowadays it's still difficult to achieve both of the accuracy and the computational efficiency. So it means, for example, when we go to the quantum wave packet dynamics, particularly like MCDDH or tensor network, we can get a very accurate result, but somehow the computational cost is extremely high. But then sometimes we have this mixed quantum classical approach or quasi-classical approach. But somehow when we're using this classical approximation, we can, computational cost is rather low, but somehow the accuracy is questionable. So in this sense, we still cannot really balance both of them, okay? So because I want to talk about machine learning, so I will briefly talk about basic concept about machine learning. So machine learning become very important research tool in the last decades, particularly due to the expansion of AI field. I mean, it's very difficult to give a very deep introduction on machine learning, but somehow I think many machine learning algorithms can be divided to two groups. Okay, like one is called supervised machine learning, another one is so-called unsupervised machine learning. Okay, anyway, there are other algorithms available. Somehow, for the supervised machine learning, this include the classification and the regression. So it's like, so you have some data that contains both of X and is labeled Y. So you want to construct the function from X to Y. So this is, for example, in the regression, you basically fix Y equal fx, okay? But somehow you also have some unsupervised learning technology. For example, you have a lot of the data, you only have X, you don't have Y. So you only want to, you can also starting from this data themselves, trying to discovering the data pattern from data themselves. This is so-called unsupervised learning. So in last few years, our group trying to focus on different aspects of machine learning and their applications to the non-adiabatic dynamics. For example, we want to trying to do the using supervised machine learning, trying to build a potential energy surface, and then we can largely speed up the computation non-adiabatic dynamic simulation. At the same time, sometimes because non-adiabatic dynamic simulation generates a lot of the data, we also trying to use unsupervised learning technologies, for example, dimensionality reduction approach, trying to really clarify which coordinate is important. In recent years, particularly, we're even trying to use machine learning technology to directly solve the dynamical evolution. So today, I think I will focus on the last two parts. Okay, so let's start from the third topic, the dynamical evolution with machine learning. Okay. So let's consider a kind of the system which is so-called open quantum system. So normally when we consider a lot of the system has many degree freedom. Okay, for example, we have to consider when we consider the photo-induced energy transfer from one site to another, from one compound to another compound. Normally, the compound, this compound normally will stay in the environment instead of isolated. So this is why the environment has a lot of degree freedom. They have a strong interaction with your quantum system. So this type of the system are so-called open quantum system. So we can, to treat this open quantum system, we can write down the total Hamiltonian as a linear combination between system Hamiltonian, Bose Hamiltonian, and their interaction. So taking the photo-induced energy transfer as a typical example. For example, if you have two compound, so after excitation, first compound, this will create a local excitation of the compound 1, and after some time, the compound 1 will be de-excited, go back to the ground state, but somehow the compound 2 will go to the excited state. So this will give us a so-called photo-induced energy transfer process. So normally when we trying to describe this photo-induced energy transfer process, we generally start from the two-side side exciton Hamiltonian. For example, we have two sides, both of them will couple the lot of the environmental degree freedom. So then we can say their evolution. But somehow we only needed to focus on the system themselves, trying to derive the equation of motion for the reduced system. Then we can basically trying to solve the evolution of the so-called reduced density matrix. So in this sense, we can fully understand the quantum evolution of the open quantum system. I think in many years, over many years, some people trying to develop the basic dynamics approach to solve all of this quantum open quantum system. Okay, so I'm trying to use two of them. One is so-called multi-layer MCTDH. Another one is so-called tensor train. I think for both of them, these two methods belongs to the so-called tensor network. So I think I will try. So I think I will try to give the mathematical detail. But anyway, let's say both of them will give us some accurate quantum evolution for the open quantum system. Although the mathematical formulas, they are very complicated. But somehow, when we apply both of them, it's also not easy to work on the real system, because first of all, we say both of them, the equation of motion can be very complicated. And also is somehow for the short time dynamics, we can easily get a converged result. But somehow if you really want to get a long time dynamics, it's very difficult to use both of them, particularly the convergence can become very difficult to be achieved. So this is why I think it's rather easy to do the short time dynamics by using this approach, but it's not difficult to really do the long time dynamics by using both of them. Okay, but I think in 2016, Cao Jianshu in MIT trying to develop the so-called transfer tensor approach. So the idea is they can, after running a short time dynamics, we can build a so-called transfer tensor model. This transfer tensor model is like a linear autoregression model, which can learn this short time trajectory data. And then using this transfer tensor model, we can predict the long time dynamics. So it means we can know the history of short dynamics history, and then we can predict the future. So later, I think they also extended this idea to other quantum classical, mixed quantum classical method, and it works well. So it means we really can try to build a model which can capture the short time dynamics propagation feature and trying to use this model to predict the long time evolution. So this is so-called transfer tensor model. But somehow the transfer tensor model is a linear autoregression model. But since this is autoregression model, we realize it is possible to introduce some nonlinear autoregression model, particularly such type of model available in the machine learning society. For example, this so-called long short-term memory recursive neural network structure. So this is the idea of recurrent neural network. For example, at a particular time, instead of only taking the input from the current input time, we also use the output from the previous time as an input to the current time. If we combine both of them, we can get the real output. So this means we can really take some memory effect into account. And also this is a nonlinear mapping model. But somehow the straightforward using of this RNN gets some trouble because it's not easy to really get this RNN. So some people propose to use a so-called LSTM cell, and then by combining this LSTM with RNN, we can easily get the long LSTM RNN. And then by using this model, we can really learn the short-time dynamics and trying to predict the future. I think this type of RNN is widely used in machine learning computing, including language recognition, as well as the financial market. For example, nowadays many people trying to predict the price of the stock market. They also use this so-called LSTM RNN. So I realized since both this neural network structure or this supervised learning algorithm is very suitable to dealing with a time series of data. So it means we can use this idea to really build a model and trying to learn a short time information, use it to predict the long time information. So this is the whole idea is going. For example, we can run the short time dynamics, and then we're trying to make create a lot of the small sequence for time series of data, and then we can be using all of this data to build a machine learning model, and then trying to use this machine learning model to predict the history, the future evolution. But somehow this idea really works well. For example, for quite some system, we can say after learning some short time dynamics, we can get a long time properly. And then in addition, for example, I really want to say here. So for example, when we're treating during this study, we also realized that sometimes because for the open quantum system, we needed to dealing with the reduced density matrix. This includes both of the information about time-dependent population evolution as well as the quantum coherence. But somehow, if we neglect the quantum coherence, can we still predict the future evolution quite well? So let's try. So now we want to really address this problem. So this is why we only consider the population dynamics instead of doing also include the coherence. But somehow we say the population, if we only include the population, the prediction is still okay, but the prediction uncertainty is very large. So this means off-diagonal element of the reduced density matrix plays a very important role in the quantum evolution of the open quantum system. Okay, so this is the whole idea, what idea is going. So up to now, well, I really want to say we're trying to build a machine learning model. So this machine learning model allow us to learning the short time dynamics evolution information and use this, and then we can use this machine learning model to predict the future. So it's like we learn history and then we know the future. Okay. And also because previously we only consider reduced the system. So when the system combined with sparse, we only have the system themselves, although the system dynamics is reduced. But somehow the problem is if we really have a huge number of freedom, can we really trying to know use this machine learning model to predict the evolution of all degree freedom in the future? Okay. So this is then we realize it is possible to realize this idea by invoking the so-called quasi-classical dynamics based on mapping Hamiltonian. I will not talk too much about this mapping Hamiltonian. So the idea is like the following. So let's consider we have the quantum system. We have several discrete level, like level 1, level 2, all of them are quantum level. Okay, so then let's make a transformation, and after this transformation, we can construct the equivalent Hamiltonian, which contain only harmonic oscillators. So if, for example, if we have two-level system, we can construct the two coupled harmonic oscillator, and then instead of running a Hamiltonian here, we can run in the dynamics for this mapping Hamiltonian, and then later we can transform back everything and get the non-adiabatic dynamics for the original system. Okay, so for here we're trying to build several this mapping Hamiltonian by using the quasi-classical dynamics. But anyway, that basically means we can run the classical. The point is we can run the classical dynamics, and finally we can go get a quantum result. Okay, and then we also trying to using this LSTM, RNN, and trying to make the prediction for the trajectory-based dynamics. So here, instead of learning short time and predict a long time, so what we are doing is we're trying to really run several different trajectory and make all the data like the small sequence of the data. And that's after constructing of this LSTM RNN, we can starting from the initial point. So let's say we're starting from the initial sampling, and with our machine learning model, we can predict the evolution of the whole trajectory. So here, only one single point is needed as an input. Then we can really predict the evolution of the whole trajectory. This include for this particular trajectory, we can predict the evolution of all degree freedom for both of the electronic and nuclear degree freedom. Okay, so now then we're trying to somehow this idea work. For example, we can using the Exciton model to start the Exciton transfer dynamics. And also we have two sides, three sides coupled with a lot of the vibrational mode, and then we can really predict the evolution of all degree freedom, including the electronic motion and the nuclear motion. And finally, afterwards, we can really get to converge the population dynamics over time. And also, we're also trying to using this approach to study the FMO system, which is a photohabitating system. And totally, we have 714 dimensions. Okay, so somehow our model can really predict the evolution of the of all degree freedom for this high dimensionality. Okay, and then we can get the converged data, and the result comparable with the original quasi-classical dynamics. And then also we tried Thales model. It also works well. So here up to now, I really want to say we built a model which is a time series machine learning model. This model can be used to directly simulate non-adiabatic dynamics. It's very promising, but somehow this I think it's also not so easy to use this time series machine learning model to simulate the non-adiabatic dynamics relativistic system. So we are still working on it. Okay. So now let's go to the second part of my talk. I will also briefly talking about another application of the machine learning in the non-adiabatic dynamics. So in last few years, our group is always focusing on the development code which allow us to simulate the non-adiabatic perform the non-adiabatic dynamic simulation of the polyatomic system. So we really want to treat the dynamics at the full atomic level. We want to build a black box simulation tool. This is like excited states MD. Okay, so we can consider we can try to using include the different initial sampling approach and also different dynamical model with different electronic structure. Anyway, so we want to create the excited states MD software. And then we also trying to investigate different kind of system over many years. But somehow, when we really simulate all of this system, I sometimes ask myself, what do we really learn? For example, we know the excited states lifetime. Okay, it's population dynamics. Sometimes we needed to know what is the geometry evolution. what is the key important evolution of the non-adiabatic dynamics. Sometimes we needed to know the reaction channel, sometimes we needed to know the physical quantities. But somehow it's not easy to analyze the non-adiabatic trajectory simulation result because we have so many trajectories. It's not easy to pick up the to know which coordinate or which kind of nuclear motion is important. So in order to do it, we're trying to combine the dimensionality reduction approach, trying to analyze the surface hopping result. So what is the dimensionality reduction? So basically the system involved, molecular system can be characterized by the high dimensional vector with a dimensionality of 3n, n is the number of atoms. Somehow if we can map this evolution of the data into the low dimensional space, for example, in a two-dimensional space, and then reduce the coordinate of this two-dimensional space automatically become the reaction coordinate. So now we can only know, check what is the reaction coordinate, and then we can know what is the leading nuclear coordinate in this non-adiabatic dynamics. So we're trying to combine this multi-dimensional scaling and the ISO map, trying to develop protocol to analyze the surface hopping dynamic simulation result. I mean, our approach can really trying to analyze a large number of trajectory and with a large system for the many degree freedom, and then we can pick up the major molecular motion automatically by using an unsupervised learning approach. Okay, and then later we also realized that sometimes it's not easy to define a single reaction coordinate if we have so many reaction channels. For example, for some system when we have two different channels, three different channels on the exciting states reaction, we can not only use one single reaction coordinate to characterize our reaction channel. So in order to solve this problem, we also trying to develop another automatic approach. We can define the trajectory similarity. So instead of only consider geometry similarity, here we also consider so-called trajectory similarity. So for example, if I have trajectory 1, 2, 3, we can really say, okay, maybe trajectory 1 and trajectory 2 are more similar to each other, but somehow trajectory 3 are not similar to them. So the idea to define this trajectory similarity comes from the mathematical field. It's like coming from functional analysis, because in the functional analysis, a French mathematician called Fréchet once defined so-called Fréchet distance. So anyway, I don't need to point out the mathematical detail about the Fréchet distance, but anyway, so they can define the distance between two different trajectories or two different lines, for example. And then we can really use this idea trying to divide the whole all trajectories, group them into different clusters. For example, some trajectories are close to each other, so they belong to
Zhenggang, please mind the time.
Okay, I think it's almost, my talk is almost over. Okay, so I think in this way we can somehow divide all the trajectories into different clusters. For some clusters, it will become the channel 1. For some clusters, which belongs to the channel 2. For each channel, we use the dimensionality reduction and trying to build the reaction path coordinate again. And also, we're still working on this part. So this means that unsupervised machine learning can really bring the considerable impact on the analysis of the non-adiabatic dynamic simulation. I think this is a fantastic field. Okay. So we also trying to, over years, we also trying to do the machine learning, using machine learning to build the potential energy surface and trying to run the non-adiabatic dynamics on top of that. And also in the last 2 years, we also start to simulate time resolved probe spectroscopy. So anyway, today due to the time limit, I will skip this topic. And also recently, we're trying to cooperate QMMM simulation into our code, and now it's possible for us to run the non-adiabatic dynamics of the isolated system in solution and also in proton. And also we're trying to combine machine learning and all of this finally this multi-scale technology trying to simulate all the time result spectroscopy. I think this will deeply deepen our understanding about photophysics and photochemistry. So finally, I would say thanks to the funding supporting from National Science Funding of China, NSCF, and also thanks my current previous group member, and also thanks for my person who make a lot of collaboration with me. So finally, I'm here, Guangzhou. So if someone wants to come to Guangzhou in the future, please let me know. So this city itself is beautiful. This is our university. Anyway, I will be happy to host any of the visitors in the future. So if someone wants to looking for the postdoc, also new assistant research assistant position, I think we also have an open position here. So thanks for your attention. Yeah.
Thank you, Zhenggang, and your inspiring talk. And due to the time limit, we allow 1 or 2 short questions. Anyone in this room? Otherwise, I put my question.
Okay.
As far as I understood, your machine learning is to predict the geometrical properties, right?
Yeah.
Can you see?
Not really. I mean, I'm using machine for one part is I using machine learning to predict the potential energy surface.
Potential
structure. But this is just one part. This is one limited part. But I think my talk today, I focus. For example, I know history. I want to use history to predict the future. It's something like that.
Can you see the hope to predict some other excited state properties?
Yeah, I think it's also it is also possible to let's say predict the excited states properties. For example, but I think this is depend on what you want. For example, if you have a structure, okay, based on structure, you can predict the excited states properties. I think we are still working on this topic now. And then, but on the other hand, while the system is moving on the excited states, its property also change, right? So I think it's also possible to predict the evolution of this property over time. Yeah, this is what I want to do. Yeah.
Okay, I see another 2 questions, and first from Pengju, please.
So hello, can you hear me?
Hello, hi. Yeah, yes, I can. Yes, thank you.
Nice to meet you, Professor Lan. So I don't think you know me, but I'm working here as a postdoc in ETH. I'm doing some chemical process by using time-resolved photoelectron spectroscopy. So I'm basically doing the comparison of gas phase trappist and liquid phase trappist. So we want to work out the solvent effect. It is exactly what you are going to do in the future, I believe. So since I'm going to set up my own group in China, so I do believe we will have a lot of collaboration in the future. But regarding this solvent effect, I'm wondering, can you also include this solvent effect, the so-called your open quantum system in your code to simulate the potential energy surfaces or some like quantum coherence, something like that?
Yeah. I mean, I think this is a very good question. So I will try to give you my understanding here. So I think when we really go to the complex system, like when we put a molecular into the solvent, okay, I think we have 2 different ways to treat the non-adiabatic dynamics of its photochemistry. So the first idea is let's go to the system plus Bose Hamiltonian. So in this situation, the nuclear motion are approximated by the harmonic oscillator. So we have a let's say electronic system and a lot of the nuclear motion. All the nuclear motions are treated by the harmonic oscillator. So then we can set up the system plus Bose Hamiltonian and then trying to solve the open quantum system. So this is the one idea to clarify what's going on. But somehow there's a second idea. The second idea goes to the last slides of my talk. So we can also try to do the so-called QMMM simulation. So the QM part is a molecular system. So the surrounding, for example, the proton or solution are treated by the force field. So this is like a multi-scale simulation. And then we can really simulate a realistic system. I mean, for both of the compound and the environment, both of them are realistic. So this is something like that. So I have my group are trying to do both of them. So it depends on what do you really want in the future. So I think if we want to, for example, know quantum coherence, or if the system like a photo-halving system, maybe the first idea is okay. If we want to really say what's going on, like isomerization, like a retinol in rhodopsin, like other photobiology, I think the second approach might be better. So this is my understanding for this problem. Yeah, I think we work for both of them. Yeah, I'm very happy to make a potential cooperation in the future with you. Yeah, thank you.
Okay, I see another question from Sui.
Yeah,
go ahead, please.
Hi, thank you, Lan, Professor Lan. Thank you for your talk. So I'm Cui Wang from University Osnabrück group. I just established my own research group since last year. So I'm basically working with transition meta complexes, mainly the first row, like the chromium or ion, or I mean the new types of photosensitizers. So I have basically a technical question about your setups. You mentioned about pump probe transient absorption spectroscopy at the very end of your talk. And I want to know, so how about the setup? So what is the time resolution of that? Is a femtosecond pulse laser, and how about the time resolution? Yes.
Yeah. I mean, I'm a theoretician. Okay, so first of all, thanks for your question. Okay, so first of all, I'm a theoretician, so I don't really care about the time resolution. Okay, because in theory we can always put up some useful laser paths. Okay, but somehow I think my focus is still like the phytochemistry laser. Because this is mainly due to the technical we are working now, because we are working on the surface hopping. We want to really treat the non-adiabatic transition for the realistic system, not a model system. Okay, and this is why we want to observe for example, isomerization and other like bond breaking, like a ring deformation. So this is why when we started off this compound, I think the lifetime this is relevant to our simulation. So we can go to, for example, like 1 picosecond or 2 picoseconds, because if we go run the dynamics for even longer, so I think the computational cost is very high. So this is why we still say I'm a phytochemistry. I'm still working in the phytochemistry region. For this region, I mean, for when we set up the laser path, I think because we are working in the trajectory picture instead of quantum dynamics picture, so this is why we make a lot of approximation to simulate a pump probe spectrum. So for example, we use this so-called doorway window approximation. This means the pump path and the probe path, they should be well separated to each other. So otherwise, the theory, the theoretical framework, what I'm using is not fully correct. So this means we cannot really use a very broad time laser. On the other hand, we also assume when the pump laser or probe laser, when they interact with the system, so the system does not evolve too quickly, because this means when this laser matter interaction can be take place within a very short time scale. So the system itself remains unchanged, something like that. So only afterwards, after interaction, systems start to evolve. So this is why we generally put the weights of the laser path to 10 femtosecond or maybe approximately this level. But somehow this will give you some basic information about what the spectrum look like. We cannot really say we can repeat the experiment, you know. So we want to get the let's say reasonable or semi-quantitative picture about what is the experiment really say. It's something like that. Yeah. Thank you.
I see. Thank you.
Okay, thank you, Zhenggang. We need to move on. Please stop sharing, and then we continue with the second.
Okay. Okay. Just a minute.
Yeah, go ahead. I have to introduce our second speaker, Professor Bin. He also one of old friends. He started his study in Beijing Normal University from 2000 to 2009. And now he is an associate professor of Northwest University, and today he will bring his recent research on the single molecule magnets. Let's see what he would share with us. Go ahead, Bin.
I need to share my screen.
Yeah.
Okay. Okay.
And please use the broadcast mode.
So, is everything okay?
And just type the play or somewhere. It's still a small screen. The first screen, something like that. Yeah, this button.
Is everything all right? Okay.
No, I still see the PowerPoint WPS screen, but not the single screen.
So, we did not show the, my slide in full screen. What?
这是播放的。
我已经选择
看一下那个，你退出一下啊，对。Do you have pressed that button, but it doesn't?
My computer, I can see my, for example, slide 2, slide 3. But in
what have you done yesterday? Have you just shared the screen or shared this program?
Right.
你可以先放到那个播放模式，然后再共享这个播放的模式。
先看一下。Okay.
Yeah, perfect.
Okay. So I can start now?
Yeah, please.
Okay, first, Happy Lunar New Year to everyone, and I want to express my sincere thanks to Mr. Wenlan Liu, the chairman of CGCA and the organizer of this conference, for inviting me to give a talk of my recent work. It's about some theoretical study of single molecular magnetic system. So we all know we are living age of data in 2020s. And some reports show that in 2020s, the amount of data we people needed to storage may be more than 40 trillion. That means almost 1,300 films in SD Blu-ray format for each person in the Earth. And hard disk drive is one most popular device for data storage. It depends on the magnetic domain, which is constructed from magnetic nanoparticle. These nanoparticles can have two different magnetic states, which represent the 0 and 1 in computer science. But there is a so-called superparamagnetic limit. That means if we want the magnetic nanoparticle have the capability to store information, it cannot be reduced to very small size. So the storage density of hard disk driver is facing a physical limit of around 200 gigabit per square inches. And the single molecular magnet is a molecular-based system which demonstrates magnetic behavior at the single molecular level. So in the most ideal case, one molecule can be 1 bit. Then the highest possible density of information storage by a single molecular magnet will be about 30,000 gigabits per square inches. That is almost 100 times improvement. Also compared to the nanoparticle, chemical preparation of molecular system will give consistent structure and composition. So single molecular magnet give us some hope to solve the challenge of storage of massive data. And the first single molecular magnet was reported in the year 1993. It's a polynuclear transition metal system consisting of 12 manganese ions of different valence states. There are two important figures of merit to characterize or measure the performance of a single molecular magnetic system. The first one is the so-called blocking temperature. It is the TB. It is the highest temperature of observation of magnetic behavior. It is quite important in real application. And the other one, the so-called effective barrier, UES, is actually the most often used ones to measure SM properties. After 10 years of the first report of a single molecular magnet, researchers found that to have a single molecular magnet, we do not necessarily need several ions in the system. We could only find one suitable metal ion, especially the less metal ion. And this system would also show the single molecular magnet behavior. The first report of this type of single molecular magnet is in the year 2003. Since there's only one magnetic ion in such kind of single molecular magnet, they are also termed as a single ion magnet. So, and then the single ion magnet gradually became the one important frontier in the field of single molecular magnet. For example, the first system with anti-barrier higher than 1000 Kelvin comes from last night, especially dysprosium-based single ion magnet. And the first single molecular system with TB higher than the liquid nitrogen limiter, that is higher than 77 Kelvin, also come from the last night-based single ion magnet. However, even the highest TB now is still far away from room temperature, and all these systems show the highest TB currently are unstable in the presence of oxygen, moisture. So, as theoretical researchers, I think maybe we could give some guide or help to find the better single molecular magnet. And we first needed to understand the microscopic processes underneath the single molecular magnet behavior. For such kind of system, their electronic states are usually doubly degenerate. And without application of magnetic field, since the two degenerate states should have equal population, and these two states have magnetic moments of same amount but opposite directions. So the system will show zero net magnetization. And then we apply the magnetic field for a long enough time, and the degeneracy of the electronic space is broken. So all the populations will go to one special state, which have certain of which the magnetic moment is along a certain direction. So the system will show magnetic moment. And then we switch off the field, the energy levels become degenerate again, but the population is not in equilibrium. And so the system will finally go back to the zero field case, which is in equilibrium. So this process from unequilibrium state back to equilibrium state is called magnetic relaxation at the electronic state level. And this magnetic relaxation is actually the microscopic process behind the experimental observation of single molecular magnetic behavior, for example, magnetic decay or the magnetic hysteresis. And the time scale of this magnetic relaxation process is characterized by the so-called relaxation time or its reciprocal relaxation rate. And to find a good single molecular magnet, we need a long relaxation time tau or short relaxation rate tau minus 1. There are several different pathways for the relaxation to proceed. The typical ones are listed in this figure, and it will increase the complexity of the study of single molecular magnet, because in principle, you need to consider all these relaxation pathways. But fortunately, the typical temperature dependence of relaxation time shows some different dependence in different temperature regions. So in high temperature regions, the behavior is determined by the so-called Obama pathway, and in the intermediate temperature region, the behavior is dominated by the so-called Raman relaxation pathway, and in the low temperature region, the behavior is dominated by the so-called quantum tunneling of magnetization, QTM, in the ground state. So maybe we could reduce the number of pathways which we need to consider to 3. The quantum tunneling of magnetization QTM in ground state and the Raman, as well as the thermally activated one, which is usually termed as about or TQTM process. And furthermore, we could further simplify the problem that we only need to consider 2 pathways. One is QTM, the other is the thermally activated ones. The QTM is characterized by the so-called QTM time. The tau QTM is later, and the thermally activated relaxation is characterized by energy barrier UEF. So we propose a simple but complex criterion for good single molecular magnet, that is the coexistence of long tau QTM and high UEF. Because if you have long tau QTM, that means the QTM relaxation will be slow. And if you have a high energy barrier UEF, that means the thermally activated relaxation will be slow. So if all the possible pathways of the relaxation are slow, so the total relaxation will be slow. If the total magnetic relaxation is slow, the magnetic behavior or the magnetic or the performance of the single molecular magnet will be better. And in the recent years, we propose some method or some working equations to calculate the 2 key parameters, tau QTM and UEF. And these equations, of course, are in analytical form. And to get the numbers, to get the values of the parameters from these equations, we need two types of values. The first are the principal T factors, as well as the energy of each prime sublet. That means all of the microscopic electronic states. And these values could be calculated from ab initio results actually. And the other type of parameters describes the internal magnetic field felt by the system, as well as the entropy of the magnetic field. And these parameters cannot be calculated directly from ab initio results, but they can be empirically estimated. So, in ideal case, for one single ion magnetic system, only one ab initio electronic structure is needed to give reliable prediction and interpretation. Of course, I have to admit that there are other methods that is more comprehensive and more accurate than the one proposed by us. For example, the method proposed by Professor Nick Children, as well as the method developed by Professor Longi. But their method usually need four parts of calculation. The first is the static electronic structure calculation carried out on crystal structure, and then the calculation of vibronic coupling or spin-folding coupling, then the formal spectrum, and finally the open system dynamics based on this metric theory. And this method, although very comprehensive, sophisticated, and accurate, but maybe the huge computation cost is unavoidable, especially for the part 2, the calculation of vibronic coupling, which might need hundreds or even more ab initio calculations for one system. What our small group want to do is to give reasonable interpretation and prediction just based on static electronic structure calculation carried out on the crystal structure. And with the equations proposed by us, and also the current very highly accurate ab initio calculation based on CGCA, with, for example, the Vocas code or OCA code, we can calculate the topology of many systems, and the other theoretical predictions show good agreement with experiment. And generally, we in more than half of the systems studied by us, we found the derivation between theory and experimental is less than 1 order of magnitude, and the derivation larger than 2 orders of magnitude is rare. Also, besides us, our method also used by different groups. For example, by the Professor of Sicily, and in their paper they also use our method, and it shows that the theoretical estimated QTM rate is in nice agreement with experimental findings. And also this work by Professor Wenlan Liu from Shenzhen University in Guangzhou also use our method to develop a new model to interpret their systems. And in the case of energy barrier, we also give reasonable results, and with quite small deviations from experimental results. So besides the predicted parameters, we can also give some mechanistic information on magnetic relaxation. And for example, based on our method to calculate the energy barrier, we can divide the temperature range into 3 parts according to the temperature dependence of the predicted energy barrier. And in the region 1, the energy barrier is nearly 0. That means the thermal activity pathway is negligible. And in this region, those QTM and Raman is very important. In region 2, we can find that the energy barrier increases suddenly. That means the thermal activity part starts to dominate or start to take control. And in the final region 3, the energy barrier becomes a saturation value, which means the thermal activity part is the dominant one. But the region 3 usually start and temperature higher than 50 Kelvin. So we think If the experimental operation temperature is at the second half of region 2 or higher, then the comparison between theoretical prediction and the experimental fitting of antibarrier is meaningful. If experimental operation temperature is quite low, then there is I think the theoretical predicted antibarrier is not obligated to be close to the experimental antibarrier. And in the year 2022, there is a very important research on the whole history of the less-than single magnet. And it gives 3 main chemical variables that determine the performance of the less-than single magnet. One is the central less-than I, 2 is the chemical family characterized based on the doped chemical strategy, for example, the geometry of central I, and 3, the element of coordinating atom. And the central less-than I should have a highly spherical electron conflict, for example, obligate dysprosium or prolate one. And there are many chemical families have been proposed, but no dominating one. Each family has its own strong and weak points. And in the case of the element of coordinating atom, most less-than single molecular magnet utilize the so-called hot donor coordinating atoms, for example, oxygen, nitrogen, carbon, or hydrogen. While examples adopting soft coordinating atom, for example, sulfur atom, are relatively rare. But there has been some reports of the less-than single magnet have direct less-than sulfur coordination. There are some examples shown here. And some work of continue a direct less-than sulfur coordination give some good performance of good single molecular magnetic performance, and so there is some optimistic prospect of such kind of systems. But we found that there is actually no clear correlation between single molecular magnetic performance and the geometry factors related to the sulfur atoms. For example, the distance of between the central and the sulfur, and the number of the sulfur atoms in the system. So we think maybe more detailed theoretical studies should be carried out in less-than single or magnetic systems containing direct less-than sulfur coordination. And we compare our computed QTM time as well as antibarrier with experimental, and we found a satisfactory consistency between theoretical prediction and experimental fitting. And the deviation is acceptable. And we also found that the best, the system showing the best single molecular magnetic behavior is just the systems which have the longest QTM and the highest antibarrier, irrespective of theoretical values or experimental fitting values. That means our proposed consensus criterion is workable here. And also we do some analysis based on the crystal field analysis. The crystal field is a theoretical model which is popular in less-than compound. And the crystal field Hamiltonian consists of the crystal field parametric BKQ as well as some common operators OKQ. So the characteristic of given less-than system is actually determined by the crystal field parametric BKQ. And this BKQ or crystal field parametric therapies could be extracted from ab initio result based on ITO, irreducible tensor operator technique. And it can also be estimated, although not very accurate, by the very simple point chart electrostatic model. And we found that for the 8 systems studied here, we could classify the first coordination sphere of the atoms in the first coordination sphere into the axial one and the equatorial one according to their positions with respect to the magnetic z-axis. The one close to the magnetic z-axis will be classified as the axial coordinating atoms, and the one which lie approximately perpendicular to the magnetic z-axis will be identified as equatorial coordinating atoms. So the right square circle the axial one, and the blue square circle the equatorial one. And in this classification, we could give ab initio crystal field parameter as well as PCM crystal field parameter. Of course, the PCM crystal field parameter is not very only semi-quantitative, but we can see that both the accurate ab initio ones and the semi-quantitative PCM one give the same general trend. And also, based on the PCM model, we could find the way to increase the single molecular magnetic performance of the system. That is, increase the contribution from the axial atom. We can reduce the distance between axial atom and the central ion. We can reduce the angle between the axial atoms to the magnetic axis. We can also introduce an electrodonating group to increase the negative charge of the axial atom. And since we could calculate the two important parameters characterize the single molecular magnetic performance of system, then we could do some ab initio magnetostructure exploration of one compound. We explore the distance between the central dysprosium line and the axial oxygen atom, and also the distance between the central electron ion and the axial sulfur atom, as well as the distance between the central ion and the equatorial sulfur atoms. And then we also change the sulfur atom to other hydrogen atom. And as showing this figure, we can show the most important one is not related with the sulfur atom. It is actually related with the axial oxygen atom. These the change of this distance gives the most gives the largest variation of the two important parameters. So that means actually the sulfur coordination is not the sulfur coordination does not play a dominant role, but only a supporting role in to affect the single molecular magnetic behavior of the system. And with this result, we have proposed some other new models which maybe show a better single molecular magnetic behavior. That is, we replace the axial sulfur coordination by some particle, for example, fluorine, the atom, or other ligand with oxygen atom. And our calculations show that this new proposed model will have a higher compared with experimental systems. These proposed new models will have higher energy barrier and longer QM time. That means these two models have the potential of showing better single molecular magnetic performance than the system 1D, which has already been reported experimentally. And this is the first work I want to share here. And the second one is the study of some tetracoordinated single ion magnet. And this work has been published last year. And we found some, we collect some four coordinated systems, and then we do the calculation, ab initio electronic structure calculation of this system to predict their top time as well as energy barrier, and to find to interpret the experimental findings. In this work, we also make some prediction of the blocking temperature, because in this paper, we also propose an equation to calculate blocking temperature based on the calculated energy barrier, as well as the based on the energy barrier. And in this equation, we use the energy barrier calculated by the ab initio result, and also the tau zero as well as this X parameter can be empirically estimated based on the available experimental data. And with this method, we predict that for this system, which is has been published in year 2021, and if the oxygen dysprosium oxygen angle could be further widened, then the blocking temperature may be increased to nearly more than 60 degrees. This is prediction of blocking temperature. That means we suggest that the experimental researchers try to widen such angle oxygen dispersion oxygen angle to get a better single molecular magnetic system. Okay, there's some take-home message. So we propose a concept criterion for good single molecular magnet, and that is the coexistence of long QTM and tall QTM and the high effective barrier of magnetic reversal in the and we give theoretical method to predict both of these parameters in analytical form. So the computational cost of this method can be minimized to one ab initio calculation for one single magnetic system. Fast application of the method in a large number of systems is probable. We can also provide some mechanical information of the magnetic relaxation, but we also need to admit that the precision of this method is limited and is maybe to give the right order for magnitude. We give some. We work on development of a single method to predict single molecular magnetic performance. We also apply our method on some experimental reported system, and we also have one perspective paper give our understanding of the interpretation and prediction of single magnetic form ab initio electronic structure. So if anyone is interested in my research, well, hope you would like to take a look at this paper. And finally, I want to acknowledge the financial support from National Natural Science Foundation of China and my PhD supervisor, Professor Yuan Huang, and as well as Professor Feng Cai, and my group and my collaborators, also my small group in Northwestern University. So, and then, thank you.
Thank you, Yinbin. Very nice talk. Now we are open for discussions. Is there any question from this room? Otherwise, I put myself.
Okay.
So, as you introduced, also as I observed, for each of your system, it's a quite challenging system. You have to put up your calculation at a rather high level of a theory, at least class SF or something even higher, right?
Yeah.
So, in the perspective of material design, do you see the hope to proceed your research somehow in a faster manner?
For the yes, the calculation is very because we cannot use DFT to treat such kind of system which is held a significant amount of configuration character, and CAS-SF may be the necessary one. But for the system studied by me, they are only contain one lesson, so the active space is only 7.5 orbitals. So that is okay for me. And actually, I showed in my electronic structure calculation on the crystal structure of system. So the computation cost is acceptable for me, but that is also the reason why the accuracy of the method proposed by us is actually limited, only right order of magnitude. If you want to get a more accurate result, and as also showing prediction, but also the cost of maybe is maybe tens or even hundreds of initial calculation for one structure, because you need to consider different vibration modes. The effect of different vibration mode on the electronic structure. So you have 3n-6 dimensions, and you need to do calculation more than that. But then recently there are some progress in this type of calculation, and someone has proposed an analytical way to calculate the space laboratory company or space form company. But that could be compared as our quantum temperature single point calculation is very fast, but the vibrational analysis is quite time consuming. Maybe other ways, but I see some they also use ways to, for example, to fit the system, or they use not ab initio calculation or some theoretical model based on crystal field to use some of fitted parameters from experimental and try to predict a newly designed system. This type of calculation will be very fast, but whether the accuracy or whether this type of method is universal, that may be an issue which you need to pay more attention.
Okay, so I see a short answer is no. I mean, whenever you talk about CASSF, no matter how small the active space is, then this is not a simple question.
But for left-hand system, is the CASSF is not so difficult because the 4f orbital is quite contracted. So it is very easy to find the suitable active space. For example, use small CAS, we do I don't need any manipulation of the initial gas. Just the default option of the program. More CAS is very good. They could give the right calculation. And for OCA calculation, maybe I need to run some DFT calculation first to get the right initial orbital to do the final CASSF calculations. But that is okay, because if you use more CAS, you can just use the default option to get the right active orbital, because you can see the final active orbital are all five orbitals of less than R. That will ensure the reliability of the calculation. I think.
Yeah, I mean, I myself is in the field. I know how difficult or how to handle this, but just to provide the general information to the general audience. Anyway, thanks a lot.
Okay, thank you.
Okay, let's continue.
Sharing, right?
Yeah, please stop sharing. And I will start to introduce our third speaker, Professor Liu. He's currently an associate professor of the South Technology University, South China Technology University. Sorry. I got to know him in 2018 when we are visiting the university with a group of German scientists. I got to know his research was quite interesting as for those so-called this radical system, but also combined with the aggregation effects. And today he will give the talk about his recent research, and he changed the title a bit, also simplified. It's called aggregation-induced radical. Moment. Is he still?
Hello, everyone.
Can you share your screen?
Okay, I will share. Can you hear me?
Yeah, clear. And then you need to use the play mode of your.
Okay. Can you hear me?
Yeah, clear.
Okay.
Perfect.
So I will start.
Yep.
Thank you so much. Thank you all. Thank you, Wenlan, to give me the chance to introduce our recent work progress. My talk is on the aggregation-induced radical. As you can see, in more than 100 years ago, the chemists have reported this kind of a diradical, and this diradical system is very, very old. And during the past more than 100 years, the chemists have published so many papers on this kind of diradicals. However, this kind of diradical are not very stable, and the researchers had many efforts to enhance the stability of this kind of diradical in the past 100 years. And of course, the stability of this kind of diradical can be enhanced. And also, they reported many potassium applications. However, you can see the DA type organic semiconductors are more interesting and more important since the Nobel Prize about 20 years ago. And this kind of organic semiconductors showed many potential applications in organic solar cells, organic light emitting diodes, and other OFET and OPD, and other kind of application fields. And the researchers usually think that the ground state of this kind of DA type organic semiconductors is closed shell singlet. And in my recent work over the past 7 years, we proposed the mechanism on the aggregation-induced radical to disclose their potential open shell singlet ground state. And while the band gap is very low, it can be the open shell triplet ground state, and it's very interesting. I will show you the main work of our group. First, I will introduce the ground state of the organic semiconductors. Second is our work on the aggregation-induced radical, and the third part is the synthesis and applications. You see, we have two questions on the theoretical fields. The first one is it is possible to that the open shell singlet ground state for all the organic semiconductors. I want to show you that maybe we can propose that all the classical organic semiconductors show open shell ground state. And the second question is, can the open shell radicals be very extremely stable? It's very important for the application of the radicals for us. And from this slide, I want to show you the two aromatic ring. This type can be donor acceptor or the other type. And you can see if we show you the quinary character of this type of organic semiconductors, we will get the two electrons and the two terminal groups. And about 7 years ago, I proposed this mechanism. And most of the scientists or the chemistry or physics field think that it is impossible because the aromatic ring is more stable. The left resonance structure is more stable than the right one. However, we focused on the study for about 7 years, and we found that it is possible. It is totally possible. And for the wide band gap organic semiconductors, it is also can be the open shell. However, we cannot detect the radical via the ESR spectrum because the theoretical character is very, very low. And but it exists, and we cannot detect it via from the ESR spectrum. And in this slide, I will show you the potential application for radicals. There are many applications in magnetics, electronics, electronics, biologics, and for example, I will show you the radicals in the field of the electroconductivity, and we can see that we introduce the radicals into the polymers or small molecules. We can enhance the electroconductivity to a very high level. You can see in this science paper, the tempo-based polymer can achieve this 0.28 is a very high electron conductivity. And the closed shell and the open shell polyaromatic hydrocarbons, you can see, and the typical organic semiconductor usually are viewed as the closed shell. For example, the polyfluorine and the typical electron withdrawing electron transport materials, and also the spiral OMe, this kind of closed shell. And this kind of materials are viewed as open shell radicals. And as I mentioned in previous slides, this kind of materials are very, very old. The mechanism is from the cis-barbene type biradicals about more than 100 years ago. And the stability of this kind of compounds are very poor, and it cannot be stabilized in air for a long time. And this slide shows the closed shelled structure of poly-PAH, and the open shell, the non-calculable structure of the polyaromatic hydrocarbons. And they will show the diuretical character in the non-calculable structure, and they should be more unstable than the closed shelled structure. And the scientists paid so many work to enhance the stability. However, they are still not very stable in air. And I will show you the ground state. The first one is the singlet, closed shelled singlet ground state. The second one is the open shell singlet ground state. And the third one is the doublet, open shell doublet ground state. And the fourth one is the open shell triplet ground state. And the third one, the fourth one is the most unstable, because the triplet ground state are more unstable than the previous three kind of ground state. And in our work, we proposed the aggregation-induced radical, and we proposed that the DA type organic semiconductors will also show the open shell singlet ground state, and it's very challenging for us and for the scientists in this field to believe that this kind of compounds will show the open shell singlet ground state. And about 6 years ago, we published the first paper in the GPCC. And in this paper, we studied several small molecules and a series of polymers, typical polymers, and we proposed that they showed open shell singlet ground state. Also, we proposed the NFA compounds will also show the open shell ground state. And as we know, the P dot and the PAM polymers show the radical cation characters. And almost none of the researchers proposed that the neutral small molecules or polymers show the radical character. And as we know, the DA type organic semiconductors are very important for OPV, OLED, and OFET in the past 20 years. As we know, the OLED has been applied in the many fields, and the other technologies are still they are very challenging to get their commercialization, because these materials are not very stable for the low bandgap DA organic semiconductors. And we think the radicals are the key points for the stability of these kind of materials. And we propose the orange of the radicals are from the open shell radical character. You see the P3HT, it shows the quinoid structure. And we know that based on this quinoid structure, we will get the two electrons as their terminal group. And from this point, it is can be easily understand that even in the P3HT, there will be the open shell theoretical characters. And in this paper, we prepared many compounds to study the theoretical characters. We found all of them are the theoreticals, and they all show the ESR spectrum. And this is a mechanism. We propose the aggregation enhanced the ICT to stabilize the theoreticals. You can see there are two ICT processes in this compound, and finally we will get the open shell theoretical resonance structure. And this is the aggregation-induced theoretical experiment. We showed that the aggregation played very key factors to stabilize the theoretical. And this is a single crystal date, and it's very solid date to support our aggregation-induced theoretical. We found that the quinoidal theoretical form from the single crystal date, and this evidence is more important and more clear for us to see the aggregate A. You can see the A dimer, the aggregate dimer A, and it's more. It shows more theoretical character than the B. As we know, the A and B is the same compounds in the same single crystals, and we found that the dimer A showed more theoretical character and more quinoid structure than the B. So this is the most. I think this is the most solid, the important evidence we can propose that the aggregation induced the radical, because aggregation promoted the quinoid structure formation and stabilized the radical. And Professor Kubo is very famous researches in this field of polyaromatic hydrocarbons, and we can see his comment. Aggregation is one of the key driving force that to stabilize the quinoid theoretical resonance structure. Is correct. For his very old system, as we know, he published this kind of theoretical, published many papers on this kind of theoreticals about 20 years ago, around, or 15 years ago, for this kind of polyaromatic hydrocarbons, theoreticals. And in their system, aggregation is also a very key factors to stabilize the quinoid theoretical. The quinoid theoretical character, because the pancake bond is very important to stabilize the theoretical. And in 2020, and this paper, the JAX paper, Professor Wang also found that this kind of small molecule also shows the quinoid theoretical. But as we know, it's very wide band gap. We cannot detect the ESR singular to conform its theoretical, but it exists. As we know, it also will show the quinoid structure. And once it's formed the quinoid, there will be two electrons at the terminal groups. However, Professor Wang forget to give the two electrons as his molecule in the JAX paper. As we know, the two electrons exist in its quinoid form. So, in the beginning of my talk, I propose that all the wide bandgap, low bandgap organic semiconductor might show the theoretical or multiple radical characters. However, we cannot detect the theoretical with the ESR spectrum. And for example, the P3HT, this is a very famous polymers. For it has been reported more than 40 years, around 40 years ago. And the P dot is also very important polymers. And both of these two polymers have been more than 30 years ago, been reported for more than 30 years ago. Recently, we prepared this kind of radicals we named them as LY1, L12, and we submitted this paper to Science China Chemistry Journal, and we're waiting for the news. And as we think this kind of really open shell, the open shell polyserine radical will be very important for this field. It can, I believe that the conductivity of this polymer can be comparable with the P dot and much higher than the P3HT, because the P3HT and the P dot show different types of diradical. You can see the diradical character of a P3HT is why we know the P dot is the radical cation type of the doped polymer. And I want to mention the pancake bond. Is in fact is very old and has been proposed about in 2009. And Professor Kober and other scientists proposed the pancake bond. The pancake bond is important for the radical chemistry. You can see the intermolecular, the two electrons where interaction, we show the interaction, the pancake interaction between the two molecules, and the ESR spectrum of this kind of diradical of the powder. In solid state, the ESR is singularly will be weak. However, the diradical, in fact, the diradical character is very high. And this is some friends of in this field comment on our work. And Professor McHoney think our work. The manuscript is a beast and so big and full of great information. And also, Kuba also support our aggregation-induced radical mechanism. And I want to mention that our AI is different from the previous 100 years of work. And you can see the stabilized driving force is different from the previous work, and also a different system. Okay, this is the previous work on the diradical chemistry, and there are so many papers on this field in the past 110 years. But in fact, this kind of diradical are very challenging to be stabilized, and our DA type molecules are more stable. And in this slide, I want to show more simple results. We propose that the aromatic ring can be can show the resonance structure of the quinoid diradical, and you can see that it's totally different from the previous work. And our diradical system will show higher chemical stability. And the third part, I will show you some other aggregation-induced radical system. For example, the aromatic inorganic acid radical. This is aromatic nitric acid radical. This is the resonance structure, and we found this type of radical showed very high stability in air, and also very high stability in electrochemical tests. And then we also proposed the aromatic inorganic acid radical, and it can be applied in other inorganic acid. And we are trying to synthesize all of these kind of radicals, and we found that they showed very interesting, very interesting properties and high stability in air. And for example, we prepared this kind of spiral 08 radical, and it showed very good stability in air, and also very good stability in the CV test. And we used this radical to stabilize the lithium calcium for lithium batteries. And for photo thermal conversion, we prepared this kind of radicals, and we found that they showed very high photo thermal conversion performance. And also in the DA pi AD type of radicals, we further enhance the photo thermal conversion properties. Sorry, and this is some results we have not published for this kind of a PTOR polymers. You see, we have prepared this kind of polymers based on this type of radicals, and we propose that they will show great application potential in the lithium batteries as cathode or anode materials for this field, and it will show very high performance and very high stability for the CV test and the batteries. And we have prepared this compound, and we got the single crystals. And in future, we will try to get this kind of a diradical, and also we are trying to synthesize the TPA O12 radicals. And we propose that this kind of radicals will show very interesting properties in the lithium batteries. And this is our results, which have not been published. We showed that the polymers based on radicals showed very good performance in the cathode of lithium batteries. It's very stable and very high capacity. And also, we show some application of the diradical in the perovskite solar cells for this kind of DAP-AD diradical. It showed a very weak diradical, but this diradical character promoted the whole transport of these materials in the perovskite solar cell devices, and showed very high performance in the non-doped whole transport materials in device, and very high enhanced stability of the devices. And I want to highlight this work. This paper has just been formally accepted in Nature Nanotechnology today, and these molecules also show the diradical character, and the researchers, the collaborators of this research showed that the very interesting results from the single molecular device, and we've also confirmed the diradical character from a single molecular devices. And in future, we are working on the synthesis of a spin pan, spin tube, and even spin ball based on our concept of aromatic inorganic acid radicals. In this paper, we propose the difference of the exciting process of a different type of ground states molecules. For the closed shell, the process is like this, and for the open shell is different. We propose the semi-excited triplet state, and we propose that there will be this process from the triplet to semi-excited triplet state to the photo-excited triplet state, and there will be also the fluorescence from the TT to T1 process. And we propose that for the NAR, OPV, and others, we should reduce the diradical characters. And for the lithium battery and other fields, for example, the superconductivity materials, we should prepare the stable radicals. And in our group, are working on this field. The most we are focusing on the OAD, OPV, and lithium batteries for the thermal conversion. And in future, we want to do some work in the superconductivity, spintronics, and device interface. Thank you so much. Thank you.
Thank you, Yuan. It's very interesting talk. I know your topic kind of well, and still through today's talk, I learned a lot. Let's see if somebody else have question.
Okay. Can I ask one question?
Yes, please.
Yeah, so in the You have a slide that show different type of radicals.
Yeah.
For example, closed shell singlet, open shell singlet, and I see that you use, for example, the up and down arrow to represent the electrons.
Sorry, can you speak loudly?
In one of your slides, you show different types of radicals. And I'm interested in the difference between closed shell singlet and the open shell singlet. So can I, can you turn to that slide?
Yeah. This one, right? Sorry.
Yes. No, the one, this one. So
this one. Yeah.
I mean, in your closed shell singlet, and I mean the figure A and figure B, the arrows, different spin occupation, the same picture, right? The figure A and the figure B.
Yeah, yeah. It looks the same picture for the closed shell and the open shell singlet ground state. Yeah, it's the same. They are the same. But
I mean, in my understanding, closed shell singlet, that means two electrons, they are paired in the same orbital. And open shell singlet, that means two electrons, they are occupying different orbitals, but they have opposite directions of MS spin.
Yeah, yeah.
So that is
usually So what's your question?
I mean, in your figure A for the closed shell singlet ground state, I think the two electrons, that means the two arrows should be placed on the one same orbital, not on two different orbitals. Closed shell.
You're right. They are on the same orbitals. Yeah.
Yeah, that is my
small error. Should put the red and the blue spins in the same orbital. This is that's what being suggested.
I know your idea. Okay. Yeah.
I mean, this should be the correct picture to present.
Yeah. Thank you.
Okay.
Usually
also, is there any, theoretical calculation of your system? Because your system is also very attractive to us who do the computation.
Great.
Especially the open shell singlet system. It's quite a much configurational character. Okay.
Yeah. Maybe just continue. As you mentioned that the aggregation is one of the key driving force to keep this diradical. And I want to know that this aggregation is really only the pi aggregation, not other kind of aggregation. Am I right?
Yeah, right. We focus on the pi stacking, pi aggregation of the polyaromatic hydrocarbons or DA type organic semiconductors. The pi. Yeah.
So it's to my somehow it's like when you combine the two molecule pi and mostly you also shift it a little bit somehow in the middle part when those it should be a two radical on both sides, so they kind of form a closed shell formation as in the middle. If this is also correct.
Right. Yeah. Right.
Okay.
In fact, in the middle, they will show the closed shell. In this kind
the middle part is really closed shell, and so due to those relaxation of the radicals on the both sides, then those radicals should be more stable if you have multiple layers, even, right?
Yes.
Yeah, which means you are to do such kind of calculations. It's more challenging.
Yeah, it's difficult to do the calculations for this system, and but the intermolecular interaction of the the pancake is very, very important to stabilize the reticle. Yeah, the pancake bound. The closed shell in the middle of these two molecules, it will show the closed shell. Something like that. The closed shell, the singlet ground state, because there are the pancake bonds between there. So that's why in many compounds we cannot detect the ESR singular, because due to the pancake bond, we cannot observe the ESR singular. Yeah.
Okay. Thanks a lot. I didn't see other questions. I shall close the session for today. Thanks all the participants, all the speakers. We shall see each other tomorrow at the same time, 8 p.m. of Beijing time. Thank you.
Okay.
And
Thank
I
you.
will close the session. And Happy New Year. Goodbye.
Thank you. Thank you. Happy New Year. Happy New Year. Bye-bye.
Bye-bye.